Mhm. All right, Mike, take it away.
Hello, everybody. Thank you for having me here today. I'm really excited to speak with you. My talk is going to focus on neural networks for graph structured data. So first off, what is graph structured data and why do we care? So a graph is a mathematical object consisting of dots called vertices and lines between the dots called edges. And these are natural mathematical models for lots of things which are important in many different areas. So for example, dots are a natural model of a molecule. Can people see my hand thingy?
Yes.
Okay. So like you could have a dot representing every atom in a molecule and then edges between these two vertices corresponding to there being some sort of bond between them. Or you could also model a social network like Facebook, where you could have a dot for every user, and then you could have links between users if they are friends. I am going to use the word vertex and node interchangeably, and also the word link and edge interchangeably. They're both commonly used terms that mean the same thing. They're also natural models for email networks, where you could have a vertex for every person, and then a link between me and Emily if Emily and I exchange emails regularly. Or you can even have citation networks, which these get a lot of attention in the research literature. Citation networks, vertices are scientific papers, and there is a link between two scientific papers if one of them cites the other. So what I'm going to do in my talk is I'm going to first give the examples of the type of tasks that we are interested in with graph structured data. And then I'm going to eventually get to graph neural networks, which are a method for solving these tasks. But first, for the sake of background, I'm going to give an overview of supervised learning and what was done in kind of traditional machine learning prior to the popularization of all of this graph stuff. And then if at the end, with time permitting, I'm going to talk a little bit about directed graphs, where some things that graphs model are naturally symmetric. If I am friends with Emily, Emily is friends with me. But there also are things where there's a natural notion of direction. So perhaps I follow Nate on Twitter, but Nate does not follow me back. And directed graphs would be used to model something like that. So there are three big overarching families of machine learning tasks on graphs. The first is graph level tasks. And here we have a data set consisting of many different graphs. And you could do things like graph classification, where every graph is a different molecule. Some of these molecules are known to be related to cancer, and others are known not to be related to cancer. And you want to develop a predictive model that will be able to tell you, given some new molecule that hasn't been studied yet, do we think it is likely to cause cancer? In addition to classification, one might also consider regression. You could be interested in, say, the formation energy of every molecule and have a bunch of example molecules where you know the formation energy and want to be able to predict the formation energy of some new molecule. And a third task, which is probably the most challenging, but potentially really rewarding if we can get right, is graph synthesis, where here the goal is you're given a data set of graphs, and let's say these graphs represent drug-related molecules. And the challenge is can we generate new graphs, new molecules that seem like they are similar in some way to all of these molecules that we know are useful for drug development? And if we could do this, then hopefully we could tell pharmaceutical scientists what studies should they do in advance and accelerate the speed of medical research. The second big family of tasks is node level tasks. And so here, typically, the data set is one big graph, and you want to consider the different users. And so, for example, you might know the political affiliation of maybe 20% of people on Facebook, and you want to develop a model which can predict whether or not one of the users who you don't know their affiliation is a Republican or a Democrat. Alternatively, you can also do an unsupervised version of this, where there's not necessarily any labels, but you would want to divide up the users on Facebook into, say, meaningful subgroups, and then you could, target ads differently to these different subgroups. The last of the three major family of tasks is edge level tasks. And the canonical example of this is link prediction. And this is something which most people by this point are very familiar with, because it's the classic example would be people you know on Facebook. So here we've got the people who are all friends with each other. And based off of our detailed analysis of the graph, there's not currently a link between Adam and Sophia, but maybe we're predicting that there should be, or there will be in the future. So I'll get into graph neural networks and methods for solving these tasks, but first, an introduction to supervised learning. So prototypical supervised learning task is you have a data set of 1,000 images, and 500 of these are cats and 500 of them are dogs. And you want to develop a model which can decide if some new image is a cat or a dog. And there's lots of ways to go about solving these problems, but many of them either implicitly or explicitly divide the task up into two halves, where you have an embedding, which you could call a front end, which creates a hidden vector space representation of every image, and then a classifier, which then tries to make a decision based on this hidden representation. And the goal is to have your embedding be good enough that the classifier's job is somehow easy. So hopefully the hidden representations of the cats and dogs will look like this, with all of the cats over here and all of the dogs down here. And then the classifier can just be, okay, look at this hyperplane. If it's on this side of the hyperplane, it's a cat, and if this side of the hyperplane, it's a dog. And the goal is to develop embeddings and classifiers which can work well together like that. So we're always treating the inputs as vectors, and we are talking about image classification. So something worth noting is that, say, a 10 megapixel image can be identified as a point in 10 million dimensional space, where each of the coordinates is the intensity of each of the pixels. And so when we're talking about image classification, we're really talking about classifying different vectors. So for this family of tasks, image classification, the networks which tend to work best in practice are something called convolutional neural networks. And this is a bit of an oversimplification, but what a convolutional neural network tends to do is it takes the input signal, it applies a linear transformation by matrix multiplication, and then it applies an entry-wise nonlinear function such as absolute value or the rectified linear unit to each component of this transformed vector. And then it repeats this many times, where in this picture, I'm only doing 2 steps so that way it fits nicely on the slide. But in principle, you could do 100 of these iterations of linear, nonlinear, linear, nonlinear, linear, nonlinear. Each of these linear, nonlinear pairs is typically referred to as a layer. This is many layers composed with or stacked upon each other, which is what leads to the term deep learning. And that's the format of the embedding. And then what the classifier typically does is something called softmax, where it y is the result of your embedding. It dot products y with some unknown weight vector, and then it pointwise exponentiates that, where e to a vector means that we are just, or wait, okay, so the probability that the answer will be equal to J, meaning if there are classes 1, 2, and 3, this would be the probability that the image is in class number J, will be proportional to the embedding dot producted with a weight vector corresponding to class J. And then the exponentiation here is meant to, it's meant to promote being certain one way or another. When you exponentiate things, it exaggerates the differences in the classes, which will tend to promote your network being more certain that it's 99% certain that it's a member of class A rather than say 75% certain. And this is basically meant to be a differentiable proxy for taking the maximum. And the reason why we want this to be differentiable is that both the embedding and the classifier are going to be jointly optimized via a process called backpropagation, which is essentially you apply the chain rule and you start from the back end of the network going forward. You start from the back end of the network and then work towards the front of the network. It's important to note that you're jointly optimizing both of these halves together. You're not just taking the best front end and pairing it with the best back end. It's all optimized as a single end-to-end unit. Now, in this picture here, A is just some arbitrary linear transformation. But in practice, what you want is you want a specific class of linear transformations called convolution. And this notion of convolution is going to be maybe a slightly different or a special case of the notion of convolution you might have seen in an ODE class, where the input signal is going to be a big picture, and the convolutional filter is either going to have a smaller shape or be compactly supported. And essentially what you do is you view this as covering a small portion of the image, and then you slide it around to capture different parts of the image. Now, there's many reasons why convolution is the right class of convolutional, is the right class of linear transformations to use. One of them is that it corresponds to sliding around in a grid-like fashion, which is the shape of an image. And the other motivating reason is that convolution has been used in image processing for a very long time. So here I've got some image of a funny looking animal. And what I can do is I can convolve it with this filter, which is something called a wavelet, and get a compressed version of this image, where this image here is mostly black, and therefore it can be stored much more efficiently than the original image because you just ignore all of the zeros. Yet you can see that this image here really does capture most of the information about the original image. The other thing you could do is you could try to post-process an image to include its quality, where here we can see that the image is blurry. And then after the processing, there's a lot more rich edges that were lost in the blurriness of the original image. In any case, convolution is well known to work well with images, and therefore it's perhaps the natural choice of linear transformation when you're doing neural networks on images. So that's the end of the brief overview of supervised learning. Now I'm going to pivot and start talking about graph convolutional neural networks, where the goal is to translate CNN principles to graph structured data. And this idea of applying linear transformation, nonlinear transformation iteratively, all of that can work the same way. But really the main thing that needs to change is what is going to be the class of linear transformations you want to apply. What is the new notion of convolution on a graph? Because sliding over a rectangle does not work. So sliding a rectangle across a grid no longer makes sense. Once you do that, you then define convolutional networks the same way as this alternating sequence of convolutions and nonlinearities. The principal challenge is defining the convolutions, which there are several approaches. There's a spatial approach, which defines convolution as a localized averaging operator. And the other approach, which I'm going to mainly focus on, is a spectral approach, which is based on a generalization of Fourier analysis through the eigenvector eigenvalue decomposition of a matrix called the graph Laplacian. So this is meant to be a generalization of Fourier analysis. So crash course on discrete Fourier analysis on n-dimensional complex space. What you can do is you can define a basis for n-dimensional complex space, U1 through UN, where the nth entry of UK is given by e to the 2 pi I n k over n, which you can think of as being sines and cosines. And then, since this is an orthonormal basis, any function on the vertex set, which can be identified as a vector, where the nth entry of a vector is the value of the function at vertex number n, can be expanded in this basis, where the Fourier coefficient is given by the inner product of the basis vector with the original function. Now, the important fact to know about this is if you convolve two vectors and then take their Fourier coefficients at frequency k, then this is going to be the pointwise product of the Fourier coefficients of the original two vectors. Turning our attention now to graphs, some notation. G equals VE is going to be a graph with vertices V1 through Vn and edges contained in V by V. We're going to have an adjacency matrix where entry JK is going to be 1 if there's a link between VJ and VK, and 0 otherwise. For now, I'm just going to assume that the graph is unweighted, just for the sake of simplicity, but everything I say can be extended to weighted graphs. Now we're also going to have a degree vector and a degree matrix, where dj is the number of friends that vertex j has, and capital D is a diagonal matrix with the vector d along its diagonals. And the other notational thing is that the neighbors of VK, the set of J such that there's a link from VJ to VK, will be denoted by N of VK. So signal processing in the Euclidean setting, we have something like a sound, and the sound signal can be decomposed into a bunch of waves oscillating at different frequencies, which this is qualitatively what's happening in discrete Fourier analysis. So in the graph setting, a function defined on a vertex set is identified with a vector on Rn. And our goal is to come up with a generalization of Fourier analysis to graph domains. And the key is going to be doing this, studying diffusions via an operator called the graph Laplacian. Although the graph Laplacian is a bit of a misnomer, there's several different definitions of the graph Laplacian. The simplest one to understand is the unnormalized graph Laplacian, which is taken simply by subtracting the degree matrix and the adjacency matrix. In all of these, though, it can be kind of understood as some sort of local averaging operator that asks how is the value of a function at a point given different from its neighbors. So here we have a graph signal. Here at this red dot, the value of the signal is bigger than its neighbors. And so the Laplacian applied to X is going to be positive there. Whereas here it's going to be negative because the value of the signal is less than its neighbors. Some further intuition is in the case of a cycle graph, where a cycle graph is exactly this thing. You can work out the computation, and the graph Laplacian will have 2's along its main diagonals and -1's off of the main diagonals. And this matrix may look familiar to you because this is exactly the matrix you would get in a finite difference scheme up to a scaling factor if you were trying to discretize the second derivative. So the graph Laplacian can be thought of as a generalized second derivative type operator. It also can be worked out that the eigenvectors of this matrix are exactly the Fourier modes from traditional discrete Fourier transform stuff. So basically, for a general graph, we are going to take whatever the eigenvectors are of L, and we are going to declare those to be our generalized Fourier modes. And it's typically common to write this in compact notation, where if UK are the eigenvectors and lambda K are the eigenvalues, you can factor L is equal to U lambda U transpose. Lambda is a diagonal matrix with the eigenvectors on its diagonal entries, and U is a matrix whose columns are the eigenvectors UK. So a generalized notion of frequency can be quantified using a quadratic form, and it can also be interpreted as a generalization of smoothness, where higher frequency waves in the Euclidean setting will look like this. Does not vary very much at all. This varies a bit more. This one varies quite a bit. And as we get lower and lower to the higher frequencies, it's varying more and more. And we can again see in the graph setting, these low frequency eigenvalues don't vary much at all, whereas these high frequency eigenvectors vary quite a lot. Formally, we define the Fourier coefficient to be the inner product of x with the UK. So if UK is our generalization of Fourier modes, then our notion of Fourier coefficients is the same as before. You can choose the UK to take it form an orthonormal basis, in which case, again, we have this formula that x can be written as a linear combination of these basis vectors called Fourier modes, where the Fourier coefficients are given by this inner products. And then in matrix vector form, it's popular to write the Fourier transform as x hat equal to U transpose x. And then there's an inverse Fourier transform given by x equals U x hat. So given this, we can then take the theorem from before that the Fourier coefficients of a convolution was the pointwise product of the original coefficients. And this theorem in the graph setting becomes the definition. So y star x is the unique function whose kth Fourier coefficient is what it needs to be in order for this convolution theorem to be true. Typically speaking, we're going to be thinking of cases where you have an input signal like x and a pre-designed filter y. So like in the image example, you had the picture of that animal, and then you had the different design filters which were meant to enhance it somehow. And so what you do is you view this convolution operator of a signal x by a filter y. You can write this formula in matrix form as U y hat U transpose, where y hat is going to be a diagonal matrix whose entries are the Fourier coefficients of y. And again, U is a matrix whose columns are the eigenvectors of the graph Laplacian. And this is exactly the class of convolutions that was used by Johann Bruna and his collaborators in their 2014 paper. That was really the first to introduce spectral methods to graph neural networks. And so this is the granddaddy that created them all, and everything else has been meant to build on this and improve some of its limitations. So one of these here is that this form of convolution, we're directly incorporating the eigenvectors, but we're not doing anything at all with the eigenvalues, because these y hats are not related to lambda in any way whatsoever. So a popular approach has been to pick the y hat matrix to be some polynomial of the eigenvalues. And the reason why you might want to do this is that when you pick y hat to be a polynomial of the eigenvalues, then it turns out that this is just equal to applying a polynomial of the Laplacian. And this means you never need to explicitly compute the eigenvectors or eigenvalues. You can perform a spectral convolution without doing this. And this provides significant savings in computational cost. And it also promotes stability and prevents against overfitting. And indeed, this was the main idea of two popular following graph neural network papers. There is Chebnet, which proposed using polynomials expanded in the Chebyshev basis. And then building on Chebnet was GCN, which is probably the most popular and widely cited graph neural network, where they made numerous simplifications and approximations to the Chebnet scheme. And they started considering, rather than a single input feature identified as a vector, a matrix of input vectors. So it's many different inputs called channels. And then what they would do is their convolution after all of these simplifications corresponded to multiplication by this matrix here called A hat. And then they did a weighting on the right to share information between channels. So the exact formula of A hat is a bit complex. What it does is they take the adjacency matrix A, they add self loops to the graph, which corresponds to adding the identity matrix. And then they compute a new degree matrix on the graph with self loops. And then they normalize this adjacency matrix on the left and the right by this new degree matrix. And essentially that's their class of convolutions. So now what they're doing is they're using fully designed filters across each channel. And the learning comes from a weighting matrix, which shares information across channels. So something I want to emphasize here is this A matrix. The only non-zero entries are going to be the IJs, such that either there's a direct link between vertex I and vertex J, or on the main diagonal. So this is going to be thought of as a highly localized averaging operator. And one of the ways you can think about this is trying to make a representation of each node where neighbors are similar to each other. So it's a smoothing type operator. And this was really modeled in the context of citation networks, where the goal is to classify a paper by subject area. And if my paper is about data science, it's quite likely most of the papers I cite are about data science. So really trying to promote this smoothness is very much a good thing. However, on other more complicated data sets, we might get too much of a good thing with the smoothness, so we can get to a problem called oversmoothing. So in the frequency domain, this local averaging is meant to promote smoothing, and it can be viewed as preserving information contained in the bottom eigenvector while depressing all other frequencies. And when you apply this over and over again, you're increasingly going to depress high frequency information. And in part for this reason, a lot of deep networks on graph are actually quite shallow. They're typically 2 or 3 layers. So there's been a lot of different solutions to try to overcome this so-called oversmoothing problem. And one of the ones which I've worked on is the graph scattering transform, where we define diffusion wavelets, where I'm sorry, this K here should be a P. But what we do is we take a random walk operator, which describes the action of a person randomly walking along a graph where they can only move from one vertex to any of its neighbors, and they do so at random. And we raise these matrix to different powers and subtract them. And the type of information that'll be captured by this wavelet will be the sort of thing like, how are my 4-step neighbors different from my 2-step neighbors? How are my 4-step neighbors different from my 8-step neighbors? And things like that. In the Fourier domain, these can be viewed as bandpass filters, where the purely local averaging operators from GCN would be grabbing eigenvectors right near the origin. And these filters like this are grabbing different parts of the frequency spectrum. In any case, what we do is we build a network that is based on these filters. And then in follow-up work, we built a hybrid network that uses both GCN style local averaging filters and these wavelet filters. And what we're able to prove is that this hybrid network with multiple different types of filters has strictly greater discriminatory power than just plain GCN. And we can introduce a geometric characterization of situations where GCN is guaranteed to fail, but scattering will succeed with overwhelming probability. And the intuition of this is that repeated applications of a low-pass filtering will eventually lead to a signal looking exactly like the bottom eigenvector of the graph Laplacian, which in the case of a normalized graph Laplacian is proportional to the degree. So it'll look something like this, where all of the vertices here that have degree 3 look the same. The vertices over here that have degree 2, these all look the same, except for these 2 vertices in the middle, where they're neighbors with both degree 3 vertices and degree 2 vertices. So they're at some value in between. But when we apply wavelet filterings, then much more differences between vertices is retained. So in the context of graph classification, if you're learning a different representation of different nodes, you have a better chance of being able to tell them apart. All right. What time did we start at?
Like 6 after.
Yeah, 105, 106.
Okay. So in any case, that was the end of part 2 of my talk, which was graph neural networks, the oversmoothing problem, and how we can overcome it via scattering. So now I'm going to pivot towards the third and final portion of my talk, which is going to be focused on directed graphs. If anyone in the audience was lost by some of the immediately preceding slides, which might have been a bit on the technical side, this is a good reset point. In any case, a directed graph is a graph where the edges have a natural notion of direction. So this would be something like citations, where my paper citing yours is not the same thing as you citing mine. Websites, there might be a link from my website to yours, but not a link back. Emails have a natural notion of direction. Traffic, if you're in a city with a lot of one-way streets. Lots of other phenomenon are naturally modeled by directed graphs rather than undirected graphs. And mathematically, this just corresponds to the adjacency matrix A being asymmetric. So we're going to have the connection that AJK being 0 means there's a link from J to K in the edge. And unfortunately, most of the graph neural network literature has focused on the directed case and the undirected case and ignored directed graphs. And one of the most common approaches to the directed graphs is just to turn them into an undirected graph by symmetrizing the adjacency matrix. And what I will say in defense of this approach is that there are a lot of situations where this actually is reasonable. Sometimes the directional information is not important. Say if we return back to node classification on citation networks, and you're trying to figure out the subject area. Well, if my paper is about data science, it's likely that most of the papers I cite are about data science, but conversely, it's likely that most of the papers which cite me are about data science. So incoming edge, outcoming edge doesn't really seem to matter. That said, there's other times where it's not. We can look at email networks where the goal is to classify different people by their role within a community. For example, there are data sets on emails within computer science departments, and the goal is to classify staff members versus grad students versus faculty, etc. And it turns out that depending on what stage of your career you're at, you have different tendencies to send and receive emails, and there is information that is useful in the direction. Another time where direction is important is link prediction. Even on these same citation networks, direction's very important. And intuitively, this should make sense because just because I wrote a paper and I cited 1 million different people, that does not mean it's some great paper that's going to get 1 million citations in the future. Those are just fundamentally different things, unfortunately. So our goal is to develop a flexible neural network model which can effectively incorporate directional information or choose not to when the data suggests that ignoring the directional information is a good idea. Some further motivation of situations where directional information is important. This is a directed stochastic block model where it's equally likely that there are links between entries of the two clusters, but we made the rule that if there's a link between cluster 1 and cluster 2, it's going to point from 1 to 2 90% of the time. And what we can see in this model example is this task here is incredibly easy if we view the graph as directed, but the second we turn it into an undirected graph, it becomes completely impossible. So this is meant to be an illustration of a time where symmetrizing, bad. A more serious example of why directional information is important comes from the Telegram data set. So Telegram is an encrypted messaging service that has traditionally been used by people in authoritarian regimes to try to be activists and promote democracy and stuff. Lately, it's been used in the West, and this data set's taken from British data by far-right extremists who've been kicked off of mainstream social networks. And what Beauvais and Grindad, researchers at Oxford, did was they made an influence network on Telegram, and they analyzed the structure of this. So for people who are not familiar with Telegram, which I'm assuming is most people, since you're most likely not watching this video in a country where the internet is restricted, and you are also most likely not a right-wing extremist. So if you're not familiar with Telegram, there's different types of nodes that could be called channels or websites, or there's actually a few green dots, which I believe are called blog posts. And this graph has this nice core periphery structure where there's a few number of channels which are at the center of the network. And then there's this like outer ring of websites which are going to be influenced by the core channels. And then there's a bunch of fringe channels that form an outer ring. Where in this context, influence is defined that if I post something and you repost it, that means that I influenced you. So the task you might want to ask is, who are the most important people? Who's likely to influence it? And without even doing experiments, it is clear that if you don't have a record of am I influencing you or are you influencing me, that this task is completely meaningless. So directional information is really important too. So with that motivation, what do we actually do? So you could extend spatial networks to directed graphs, and spatial networks are typically revolve around localized neighborhoods, which are still well defined. The problem is that the VJ such that VJ, VK is an E are no longer the same as the vertices where VK, VJ are in E. And we have to make some sort of like completely arbitrary choice. And so with spatial approaches, they're well defined on directed graphs, but they don't work well. And indeed, this is why symmetrizing is such a popular option, because it does tend to improve performance. With spectral approaches, the challenge is that it's not entirely clear how to generalize the graph Laplacian. And so we're going to propose a method based off of a complex Hermitian matrix known as the magnetic Laplacian. And our idea here is that we're first going to develop a complex Hermitian adjacency matrix. And the undirected geometry is going to be captured by the magnitude of every entry, and directional information is going to be captured by the complex argument. So this is basically a polar coordinates type expansion where you incorporate the presence of an edge and the direction of an edge separately using the magnitude and the direction in polar coordinates. These matrices are going to have a parameter Q, which is going to range between 0 and 0.25. When we set Q equal to 0, it turns out that all of the phase information is destroyed and we treat the graph as undirected. Whereas when we set Q equal to 0.25, then it's going to be skew symmetric. So a link from me to you is the opposite of a link from you to me. Then given this complex Hermitian matrix, you can then define normalized and unnormalized magnetic Laplacians by formulas similar to the classical Laplacian, where you take degree minus this new adjacency matrix. And we like using Hermitian matrices because complex numbers are good, and we can use polar coordinates to represent magnitude and direction. There's a good question, which is why this particular Hermitian matrix? And I claim there's at least 3 different reasons. One is it does naturally appear in the physics literature as a model of a charged particle going under electromagnetic flux. So it is something that exists in nature, and it was not just made up by mathematicians, sitting in some dimly lit room late at night. There's also has been a lot of theoretical research into it by the graph signal processing community. So if this network became very popular, we'd have a good chance of understanding it. And prior to graph neural networks, it's actually been used for a bunch of other data science tasks, such as clustering and community detection. I'm running a little bit low on time, so I'm going to go quick. But in the case of a directed cycle, the eigenvectors are exactly classical Fourier modes, and the eigenvalues depend on this charge parameter. And in the case of a directed star, it's the opposite, where the eigenvalues are unaffected by the charge parameter and are the same as in the undirected case, but directional information is captured in the eigenvalues. And what these two examples are meant to illustrate jointly is that both the eigenvectors and eigenvalues are important for capturing directional information. But in any case, what we do is you take your favorite spectral graph neural network and you use the magnetic Laplacian in place of the traditional Laplacian. And then you mostly do everything the same way, except you make various adjustments to account for the fact that you're dealing with complex numbers. In the final step for the classifier, you have to separate out the real and imaginary part. You also need to use a modified version of the rectified linear unit to account for complex numbers. But mostly the take-home message is take your favorite neural network for graphs, use the magnetic Laplacian in place of the traditional Laplacian, and it's very much plug and play, very flexible. Some alternate approaches are to develop networks based on random graphs. And these networks can also work quite well in a lot of applications, where what they typically do is they work out some sort of algebraic relationship between random walks and the graph Laplacian, and then they try to extend that to the graph setting. And sometimes they will use PageRank rather than a random walk. But what we do see is that these methods based on magnet generally for most of the data sets we consider tends to outperform these other neural networks for directed graphs, which are typically based on random walks or a few other tricks. And what we also see that's quite important is that with the exception of Cora, which Cora is a citation network, where I previously have said that it's intuitively clear that directional information should not be important, that our model is selecting a non-zero Q value. And non-zero Q corresponds to the network learning through cross-validation that directional information is important and symmetrization is not the way to go. We also did experiments on link prediction. And here again, we see that for all tasks, directional information is important, even when we're using these citation networks, where for node classification, vertex classification, we found that directional information was not important. So looks like I am out of time, so I'm going to stop here. But in conclusion, convolutional neural networks are great for a wide variety of machine learning tasks, and they can be extended to graphs using the eigendecomposition of the Laplace operator. Most GNNs suffer from two limitations: oversmoothing and the inability to process directional information. And the solutions we are proposing are the graph scattering transform and networks derived from that, which use bandpass wavelet filters, and magnets, which generalizes GNNs to directed graphs by using a complex Hermitian matrix. And that is where I'm going to stop. Thank you very much for having me and listening to me talk.
Thank you so much, Mike. Let's all thank your speaker. Cool. I'm now going to stop the recording.